Today, we're diving into something that sounds, well, just plain wrong. It's an idea from the world of aviation safety that's going to flip everything you think you know about maintenance completely on its head.
I mean, it sounds crazy, right? We all think of maintenance as the thing that keeps us safe. It's the ultimate safety net. But what if the fix is actually the thing that breaks it? This is the core paradox we're going to unpack.
And get this is not just some philosophical puzzle. The data is pretty sobering. Aviation safety experts tell us that maintenance-related factors are a contributor in a staggering 15 to 20% of all aviation accidents. The stakes could not be higher.
So, how on earth does this happen? To really understand it, we need to look at a specific phenomenon that engineers and safety inspectors are constantly fighting against. It's called a maintenance-induced error, or MIE for short. The idea is as simple as it is terrifying. You take apart a perfectly good component to inspect it, but in the process of putting it all back together, you accidentally create a brand new, hidden flaw. The cure, literally, becomes the disease.
What makes these MIEs so incredibly dangerous is that the damage is often latent. It's hidden. We're not talking about an obvious mistake, like leaving a wrench in the engine. No, this is much, much sneakier. It's an undetected stress crack, a bolt tightened just a tiny bit too much, or a little piece of debris left behind. It's a ticking time bomb that might not go off for hundreds of flights, which makes it incredibly hard to trace back to that single moment in the maintenance hangar.
So, where did this risk even come from? Well, for a long, long time, the entire philosophy of maintenance was built on an idea that feels very intuitive, but as it turns out, is deeply flawed.
This was the hard time philosophy. It's the same logic we all apply to our cars, right? After a certain number of miles, you change the oil, period. In aviation, this meant replacing complex parts at fixed intervals, just based on flight hours. The belief was that older is always less reliable. So they thought more intervention must mean more safety. But then, when researchers in the 1960s actually started studying the data, they found something that was a total shock. Everyone just assumed that older parts failed more often. But the reality, especially for complex systems like engines, was that after a short break-in period, the failure rate was mostly flat. The parts simply weren't wearing out in that predictable way everyone thought they did.
Now, this flawed hard-time way of thinking, combined with the constant pressure for efficiency, created the perfect storm for one of aviation's most infamous disasters.
The date was May 25, 1979. American Airlines Flight 191, a DC-10, crashed just moments after taking off from Chicago. All 271 people on board, plus 2 more on the ground, were killed. And the cause wasn't some hidden manufacturing defect or pilot error in the way we usually think of it. The root cause was maintenance. You see, to save about 200 man-hours per plane, American Airlines had come up with its own shortcut for removing engines for inspection. Instead of taking the engine off the pylon and then the pylon off the wing, they were using a forklift to take the whole thing off at once. It was faster, it was cheaper, and it was incredibly dangerous.
That flawed procedure was the hidden danger just waiting to happen. But the active failure, the thing that lit the fuse, happened when the maintenance crew, under pressure, didn't even follow that non-standard procedure perfectly. The forklift wasn't positioned exactly right, and the massive engine and pylon assembly twisted as it was being moved.
That small rotation applied an immense force to the pylon's attachment point, creating a huge 10-inch crack in a critical part of the structure. And the scariest part, it was completely invisible to the naked eye. So, the maintenance was signed off, the engine was put back on the plane, and a catastrophic failure was now locked in, just waiting for takeoff.
The official accident report makes the connection crystal clear. That push for efficiency, the shortcut designed to save time and money, created a direct path to this disaster. The very act of maintenance, done improperly, doomed that aircraft.
The lessons from Flight 191 and all of that groundbreaking research forced a complete revolution in how we think about maintenance. It led to a much smarter, data-driven system.
This brings us to something called the bathtub curve, and it's one of the most important concepts in modern reliability. It shows that failure rates aren't a straight line. There's a high rate of failure right at the beginning, then a long, stable period of normal life, and then finally, a wear-out phase at the very end.
That initial spike is called infant mortality. These are failures that happen early on, often because of tiny errors made during installation. Which means, and this is key, that when you install a brand new part, you are actually in the most dangerous phase of its entire life.
And here it is. This is the big aha moment of this whole explainer. The old hard time philosophy was taking perfectly good components that were operating in that long, stable, low-risk part of the curve, and by removing and reinstalling them, it was forcing them right back into that high-risk infant mortality phase over and over again. Unnecessary maintenance was actively increasing the chance of failure.
This table here shows the evolution, just beautifully. You start with hard time, assuming wear out is going to happen, which introduces a high risk. Then you get a little smarter with on condition, where you inspect things and only act when you see a problem, much lower risk. And finally, you get to the modern approach, MSG3, which assumes parts are reliable to begin with and focuses on eliminating needless tasks altogether. And that minimizes the risk to almost zero. And that's MSG3, the modern standard. It's a philosophy built on a simple but incredibly powerful idea. Don't touch it unless you absolutely have to. You use data and you monitor the condition of parts to justify every single intervention, making sure the risk of doing the maintenance never outweighs the risk of a failure.
So, after all of this, the flawed assumptions, the tragic accidents, the data-driven revolution, what is the ultimate lesson here?
It's this. Safety isn't achieved by doing more maintenance, it's achieved by doing the right maintenance. The safest action is often the one you don't even have to perform. If you can eliminate an unnecessary task, you eliminate the opportunity for an error.
This leads to 3 really clear principles. First, constantly question if a task is truly needed. Second, for those tasks that are necessary, standardize them rigorously, no shortcuts, ever. And third, trust the data. Monitor the actual condition of a part rather than just replacing it because of what the calendar says. And all this leaves us with a fascinating final thought that applies to so much more than just aviation. In our incredibly complex world, from managing technology to our own health, we have this bias for action, a desire to always intervene and fix things. But maybe the most important lesson from a century of flight is learning to recognize when the smartest, safest, and most effective action is to do nothing at all.